Topic of today is extending the trig functions in such a way that we can handle angles that are bigger than 90 degrees. Do you recognize that particular poverty of your definitions from yesterday and from geometry? Do you recognize that poverty? That like you can't be asked right now with those definitions what the cosine of 100 degrees is or something. You recognize that you can't do that using those definitions. Well, I know. I'm just saying, using the definitions from yesterday, at least, that's not a thing you can do.
Yeah.
That's not the subject of right triangle trigonometry. Before we get too far into this, we need to establish some kind of common ground about how we talk about angles. This would be the kind of thing that I'm sure you would have encountered maybe in a previous class, but we're going to put up an angle right now in what's called standard position. So the initial ray of the angle is along the positive x-axis. This is how we often picture it when we lay it onto the coordinate system. And then we have the angle opening counterclockwise, and then the terminal ray will be wherever it is. And we consider that the angle in the positive sense. So the counterclockwise direction we consider to be positive. Is that like an arbitrary decision? Yes. That's just what the whole mathematical and physics community, everything is decided. And that's what we mean by positive. Counterclockwise. Notice, of course, that we can have angles now that are not just bigger than 90, but also we can think of angles being bigger even than 360 when we think about, obviously, again, like we said the other day, we can't find an angle bigger than 360 in a while. But when we think about rotation, then maybe we can. And if that's the case, if we can think about rotations, then not only do we have angles bigger than 360, we can also think about negative angles, right? That is, angles that open clockwise instead of counterclockwise. Two angles are coterminal if they have the same terminal ray when they're put in standard position. How could it be that two angles could be coterminal without actually having equal measures? Give some reasoning about that, Stephanie. Say it one more time. Okay, give an example. Right, so 30 degrees and 930 degrees looks like this. Yeah. 390 degrees looks like that, right? Back home. Yeah. But they have the same, they don't have the same measure, but they have the same terminal ray when put in standard position.
You also have like 90 and negative 270.
Yeah, 90 and negative 270, right? 90 versus negative 270 looks like that, right? Good. Oh, we didn't go over the warm-up. Is this right? Did she do a good job? Okay. Done. There are many ways to do that, by the way, of course. Inverse sine is not the only way. Okay, so, I don't know, taking Stephanie's logic here and going with it, let's do that. Let's actually find some examples of some coterminal angles with the following angles. Yeah, bonus points if you know the Greek letters. What's this one? Gamma. Good, gamma and beta. Phi, yeah. Who said that? Or phi. They're both fine. They're both fine. Yeah, phi or phi. Last one, good job.
No.
You do not need to know them necessarily, but it's kind of fun. It makes you sound smart. Okay. So now do what we just said. Find. I'll call on people in a second. Give me two coterminal angles for each of these that isn't the one listed. That are one that's positive, one that's negative for each one of these. I'll call on some people in a second. So get the first one. You might still be working on the third one, I'm sure. Emily, do you have some angles to the first one that work? What are some that are coterminal to 35 degrees? Negative 325. You got another one? Give me a positive one, too. Do you guys agree? Okay. How about Stephanie? Give me B here. Negative 480. It's okay. Arithmetic, man. And 210 agree, class? Okay. Good. And there are others too. Obviously, you could say on any of these, there's like an infinite number of correct answers to these. Like, give another one here. What are we? 570 would be a fine answer as well, right? Those are the two that they first gave. Are probably the ones you had too, though. Okay, but certainly there are other correct answers. And then, you know what to do on C there, Louisa? Oh, because it's in radians. Oh, okay then. Go ahead.
I got 8 pi.
So you're adding 6 pi over 3, which is 2. Okay, I'm with you.
And minus.
Good. Again, infinite number of options there too.
So if I was doing C and I answered in degrees, would that be wrong?
I think it's I don't know why. Why would you do that? Maybe. Oh, because you like 2 pi. It's one you know. You're like 120 degrees. Did you say that right away or something? Okay, I see what you're saying. I think it suggests that, I don't know. I guess it's okay. It does seem like someone might like the answer in radians. But
Oh, so like both are exactly.
I guess so.
Or radians like makes more sense.
I don't know. It makes me happier maybe. But I guess it didn't explicitly say something. I don't know. Now we're splitting hairs. Do you think we could write down every single coterminal angle all at once? Yeah, maybe we could write it this way. 35 degrees plus 360 times n or something, right? Where n is any what? Not any real number. Any integer. So for example, if you don't believe me that I have every single one written down now, if n is 0, that's an integer, then we get this angle, the original one. If n is 1, we get this angle. If n is negative 1, we get this angle. And if n is any other integer, you get every other thing that would be on someone's list. So that's kind of nice. Or over here, for example, we could say 2 pi over 3 plus 2 pi n, where n is in the integers. Right? It's the same kind of thing, though we've just done it. We've named them all, right? Mic drop. It's like, did you have another one that's not on that list? No, you didn't. Let's move on. Okay. Right? Is that a cool way to do that? I like that. Thank you, Neil. Appreciate you. All right. Now I think we're finally ready to actually say what the definitions are of the trig functions. Here's the thing we should start with. We should start by thinking about our angle in standard position. There it is, theta. And start by putting a point on the terminal ray, anywhere you like. Call it x comma y. Anywhere you like on the terminal ray. And now I will ask you, what would you like the definition of, I don't know, sine to be? Do you have a suggestion? You can rely on previous knowledge if you know the definition of sine. Does anyone know the definition of sine? No? It's not quite y, given that the fact that y, but I like where you're going with this, right? Because y changes, and we want this to be invariant based on the angle, right? Like we don't want it to be dependent on where we are necessarily. But I like y in another sense because it does still capture the height, right? It kind of captures the height. So I like your suggestion. You want to revise it, Brandon?
Look at the slope.
The slope?
Yeah. Because it's like x and y. And that's always going to be the same ratio.
Oh, I kind of like what your thought is. What is the slope? If this is the point x, y, what's the slope of this line? If it goes through the origin,
Y over x.
it's y over x. But But y over x does give an invariant quality. Like regardless of where x and y are along the terminal array, you'll always get the same ratio. That's an important ratio, but it's not sine. Which is that? That's tangent, y over x. In the first quadrant, can you see y? If you're over here, y divided by x would be like, if we were in the first quadrant with an acute angle, it would be opposite over adjacent. So y over x is an invariant quantity. It's a nice ratio, and we have a name for it. It's called the tangent. All right, we still haven't said what sine is, though. You want to give it away, Jade?
Sine is y over r.
What's r?
The ratio.
What? There's no r? Oh, wait, now there is. Okay. Yeah, r, we'll call this distance here, which r can be gotten by, how do we get this? The square root of x squared plus y squared? How do we get that distance? That's just the Pythagorean theorem or the distance formula, whatever you want to call it. All the same thing, of course. So compute r, which is the distance you chose the point to be away from the origin, I guess. You pick the point, you can figure out how far away it is by using the Pythagorean theorem. It's always going to be the square root of x squared plus y squared. Let's, for the time being, call that r. And then say again, what's sine, Jake? What'd you say? Y over r. Now in the second quadrant, maybe that makes sense. In the first quadrant, does that agree with our old definition? If we're here, y divided by r. Does that make sense for the sine if we were back in the old definition? Opposite over hypotenuse. So I think it does make sense. If we're back under the old definition, it works out, it agrees. So that's good. So those are the definitions, and I think you would have remembered those from last year. Is this a thing that you learned? I think, and all of you had trig at one point, so it should be somewhat recalled, but maybe it's been a while. So these are all the new definitions. Yeah.
So r is just like the distance from the point to the origin, like that.
Yeah. So, like, it was a fun lesson yesterday, but you can throw away all those definitions if you never need to use them again ever, right? Like the sine of an angle from now on, well, even if you're in the first quadrant, is y over r. Now notice that r is always what kind of quantity? X, the square root of x squared plus y squared will always come out to be a positive number, right? So if you're doing y over r, how could sine of an angle come out to be negative? Could it come out to be negative? R is always positive, but could y be negative? When? Yeah, if the angle has a terminal ray in the second or in the third quadrant, exactly. So when does the sine of an angle come out to be negative? Well, when we're down here, exactly where y is negative. What about cosine? Where is that going to be positive versus negative? It's exactly when x is positive or negative from the definition, right? So cosine will be positive when an angle terminates in the first or the third, or the fourth quadrant over here. Because isn't that where x is positive? Over here. And it'll be negative. This will come out to be a negative number when the terminal ray lies in the third or the second or the third quadrant, right, over here. Because that's where x is negative. That's just how it is. And we could do some analysis on tangent too, if you like. But let me say one more thing about this picture here. Some people like to think about something called the reference triangle. It's not necessary at all, in fact, ever, if you think about this. But I'll just draw it in case you like to think about it this way. This is a somewhat trying to like squeeze the geometry definition in here. We're still like, you really don't want to let it go, I guess maybe, is why you might think this through. So if you drop from your point down to the x-axis, or if you're below the x-axis, up to the x-axis, but drop it to the x-axis, you form a little triangle here. And as long as you're okay with the following two lies, then like the reference triangle maybe gets you the same answers. The first lie is that this is the angle we're talking about here, but really we're not talking about that angle. We will want to be speaking about this angle. The second lie is that like what's the cosine of this angle going to be? Well, it's going to be something negative. Right, it's negative x. It's like a negative x value. That's the second lie, is like, are you okay with negative side lengths of triangles? Like, okay, if you swallow both of those things, then like reference triangles might be a thing you could think about and it might be for you. And then it still is kind of like, what's the cosine of this angle? Well, this angle. Well, it's still kind of adjacent over hypotenuse, except we're talking about that angle, not this one, and it's negative. As long as you're okay with that, then. I don't know, that might be a way you thought about it in algebra 2, though. Have you thought about this reference triangle thing? I think you have maybe. like we've already said this, but if we're in the first quadrant, of course, these do perfectly align with our old definitions. Really, the definitions you have in life really should feel that way, right? As you go from one course to the next. They should be backwards compatible, right? Like Microsoft Office 2010 should be able to open 2007 like Word documents, right? Like you hope that that'll be true. Like when they backwards compatible. Like the old definition works, but the new one is like better. They're like it's backwards compatible. Right? You might be thinking too, like, is there yet a more expansive definition of these trig functions? And the answer is like yes. For complex numbers, you'll have to like wait till like very later, much later in your mathematical career to learn how to take like the sine of I or something like that. And those are once again backwards compatible down to the other two. So, but for now, this will be good. All right, I don't want to trouble your hearts with all that. All right, what? That's our favorite letter right there. Omega. Yeah. Okay. So -5, 3. Now this is very similar to the picture I had up here a second ago. We're in the second quadrant. 3, 5, 1, 2, 3. So you might start by drawing a picture. There's the picture of omega. All right. We'll find all 6 trig functions evaluated at omega. What do you need in order to do that? You need, go back to the definitions on the previous page. You need x, y, and r. X and y are there for the taking, because I gave them to you. R you need to compute, so that will take you only a second. It's not nice, just, you know, you better if you're finding R.
Oh, I get it. Oh, wait, no, I don't. I thought I did.
Trig.
No.
So what do you get for R? What's R come out to be? Yeah, square root of 34. And that's a fine way to leave it. Just leave it as root 34. And we'll use that now and all. Now we have everything we need. We have x, y, and r. Just go back to the previous page where we define these and just copy them down. So walk us through these. How about Samantha in the back? Ready? Give me sine, cosine, and tangent. You do those 3. How about? When you're ready.
Sine would be 3 over square root of 34.
Mm-hmm.
Cosine would be -5 over square root of 34. And tangent would be 3 over -5.
So far so good. You see where she's getting this? She's like literally copying off the last picture. Like, okay, sine is, yes sir, it's y over r. Whatever you say. And Vicky, you want to get the other 3? Root 34 over 3 is in fact the reciprocal of that. I agree. What's the name of that function? Cosecant omega. Yeah, keep going. You're doing great. Yeah, negative root 34 over 5, and finally good. Questions? Thoughts? Comments? You okay with, you like those definitions? X, Y, R.
So is it possible to like find this with an angle that's like greater than 360, like 540?
Absolutely, yeah. Where you just need to find a point on the terminal ray and run this. Yeah. A point anywhere you like. Now, if if you were a sly person, you might be thinking, wait, really? Do I have the choice of putting x, y anywhere I like? Then what would be a really nice, slick choice for r? You can choose at the distance you want. 0 becomes degenerate because then you're dividing by 0 on these definitions. So that's not useful. Yeah, let's let it be 1. And what we get here, if we do that, is the same picture as before, except this distance here, by your choice is 1, right? There's no reason you can't ever make this true. You know, you could just declare that to be true. I told you you can pick a point anywhere along here you like, and you've done it. You've decided that you want to pick the one that's exactly 1 unit away. Why is that a really nice choice? Why is that a really nice choice? What happens, Antonio?
I think now it's like 36 triangle.
Well, not necessarily. I didn't say what angle this was.
Well, the hypotenuse is 1,
True.
which makes me believe.
But it could be anywhere, right? It could be anywhere. In fact, it could be anywhere on this circle, that point, right? But it's called the unit circle, by the way. Yeah, so. Yeah, where are you? Was it Neil? Did you say? Yeah. So now we come back to Neil. He said earlier the definition of sine is y. Yes. Now we can say if we're at a point that's 1 unit away from the origin, then yes. So now, again, if xy is a point on the unit circle, I just want to caution you there again. Like if you tried to do the last problem after seeing this definition, you might be like, oh, the sine is 3. No, in fact, the sign will never be a number in absolute value greater than negative or positive 1, right? It'll be greater than 1. So yeah, this simplifies, like Stephanie says, this really simplifies our definitions quite a bit. And furthermore, if this is the point x comma y, and x is just cosine theta, then if you're a point that lives on the unit circle, if that's where you do business, you live on that unit circle, then your coordinates, if you know your coordinates, if you know the coordinates you are at, then you know the cosine and sine of your angle. In fact, there's just no work to do. They are your coordinates, right? Which is very nice. If you know the coordinates of a point on the unit circle, then you know immediately, without any work, your cosine and your sine. That's such a beautiful and important property. That we're going to just like stay there and live there for a while, right? We like that idea. We like the unit circle. It makes everything nice. All right, so the thing I've just given you, and it's up here on the board too, is the unit circle again with, and you can see that it's the unit circle, right? Radius is 1, that's the point 1 comma 0, with a whole bunch of common points labeled. Sometimes I think your book calls it the 16-point unit circle. Because there are like 16 very nice values. You could label other ones. There's nothing sacred necessarily about these points. They're just ones that we kind of expect that you know and love. And then immediately you would know the sine, cosine, tangent, etc. of. Okay? So I think it's a picture you've seen before. Based on, Reggie will tell you that this coordinate, if this really is 30 degrees, then this definitely has the coordinates root 3 over 2 and 1/2. Because this is 1, and that's a 30, 60, 90 triangle. So see yesterday, if you want any justification for why this point is root 3 over 2 comma 1/2. Or see yesterday, just to have any justification for why this coordinate must be root 2 over 2 comma root 2 over t2. And then how do you get all the other points? Just by symmetry, right? So that then, of course, this point has the same, if this is 30 degrees and this is 30 degrees, then there's symmetry there. So it has the same y coordinate and the opposite x coordinate, all the other points you can get. So when it comes to, I don't know, there will come a time here when you're like, oh, I have to memorize this. Well, do you though? I mean, how much do you really have to memorize. I mean, these 2 points maybe, and even those you could quickly rederive in a moment's need, right? Just draw the triangle, be like the Pythagorean theorem. Of course, again, you could solve for those values again if you really need to. There's really nothing to memorize per se. You want to get more proficient at it, but it looks like you're like, really? I have to have all of this eventually? This needs to be in my head? It's not actually a hugely tall order, so I think that's okay. Let's illustrate how this can work to calculate some of these values, for example. Like say you want the sine of 2 pi over 3. Yeah?
Does it matter whether you write it as root 2 over 2 or like 1 over root 2?
Doesn't matter. Sine of 2 pi over 3. So the first thing you would do is locate 2 pi over 3 radians. And then what's the sine? What's the sine? Keep in mind that if you're on the unit circle and you have these coordinates of points 1 unit away, then it is just the y coordinate, right? There's just no more work to do. Root 3 over 2. Positive, you know it's going to be positive because it's the y value divided by 1, right? Root 3 over 2. What about the tangent of 3 pi over 4? Well, 3 pi over 4, similar area here. We're here. What's the tangent? The definition of tangent is y over x. So what do we get here when we divide this thing by the exact same thing, but it's the opposite? We get -1. And in fact, let's stop and say, where will tangent be negative? Certainly here, I guess. Right, where y and x have opposite sign, or here, and here what's happening? Y and x are both negative, and so tangent comes out to be positive just as it did here. All right, so just make sure you're seeing those things. Cosine of 11 pi over 6, that's here, 11 pi over 6. So what's the cosine? It's the x coordinate, right? Root 3 over 2. Do you see how this is going to work? If you know the coordinates, then these answers are pretty quick. Now, let me go back to the slide quickly here. How do we remember where the angles are, though? If you're going to commit this to memory, you also have to like quickly locate 3 pi over 4. Is that here? No, it's here. All right. So how do you figure that out? Well, let's start with the pi over 6 ones. All the pi over 6 radian measured angles, pi over 6, are highlighted right now. You see them? So they're all the ones that are low and tight, close to the x-axis, right? X-wing style, right? You see it? Coming at you. That's where all the things over 6 are. Pi over 6 is, of course, the first one. 5 pi over 6, how are you going to remember the ones in this quadrant? This is 3 pi over 4, 2 pi over 3. How are you going to remember that?
I just do it using like the fraction. So like, for
Yeah.
example, like 5 over 6, if you visualize just that the top like semicircle of the unit circle, you just go every third of it is pi over 6. So 5 pi over 6 would be almost all the way down to pi.
Yeah, just like pi over 6 away from being all the way to pi, right? Yeah, exactly. Or if you're just thinking numerically, these numbers in the numerator are exactly 1. The coefficient on pi is exactly 1 less than the denominator. Do you see that? So even if I give you an angle that's not up here, like 12 pi over 13, you're like second quadrant, right? Okay. Yeah, Neil.
This is related. What would be the tangent of like 90 degrees?
Yeah, what's the tangent of 90 degrees? What's the definition?
Sine over cosine?
It's y over x. So what is it there? What's 1 over 0? Undefined. Yeah. The pi over 4 ones are like right here, right? X-man style. All the X, right? X-man style now, right? Just a big X. And I don't have a name for this, but these guys here, all the pi over 3s are here. Really close to the y-axis. We're gonna practice this so you're blue in the face. We're gonna get good at it. Homework 4 tonight. Have a great weekend.
Wouldn't it be 1/2 of